Okay, welcome everyone to HO colloquium today, the special colloquium. But it is our great pleasure to introduce Nobumitsu Yokoi from University of Tokyo. He is our speaker today. Um, Nobu Yokoi is a physicist working on analytical theories and modeling of hydrodynamic and magnetohydrodynamic turbulence. He got his PhD in 1995 at Department of Physics, University of Tokyo, with the work on helicities, relationship of pseudoscalar invariants with the sustainment of global structure in hydrodynamic and magnetohydrodynamic turbulence. With the aid of the multiple scale direct interaction approximation, a combination of renormalized perturbation expansion theory and multiple scale analysis, Nobu has explored the turbulent fluxes in inhomogeneous, anisotropic, and non equilibrium turbulence from the fundamental equations. His interests range over the formation of large scale vertical structure, turbulent dynamos in geophysical and astrophysical bodies, magnetic reconnection in turbulent media, transport separation in fusion and engineering devices. The electromotive force, mass and heat transport in strongly compressible MHD turbulence, angular momentum and energy fluxes in stellar convection, shockwave turbulent boundary layer interaction. He has collaborated with lots of applied mathematicians, physicists, astrophysicists, space and fusion plasma scientists, engineers, as well as solar physicists. Today, uh, Nobu will be speaking on Helicity turbulence model, validates applications to stellar angular momentum transport.
Okay, thank you. Thank you very much for very nice introduction. And I really appreciate you inviting me and giving me this opportunity. So today I will talk on this topic. And this work, part of this work is in collaboration with Pablo Minini and Anik and Duane Rosenberg and Rafael Manino and Mark Misch. Okay. So then this is the content of my talk, hopefully. And then first I will very briefly introduce very basic things about the kinetic helicity, not magnetic, kinetic helicity. And then I will talk very briefly about something I think very important on turbulence transport. Then kinetic helicity effect, and the first point is helicity subgrid scale modeling and its validation, and stellar angular momentum application to stellar angular momentum transport problem. I think which is a main interest in this institute. And then if I have some kind of very new one, scalar flux in homogeneous turbulence. I think final one is very interesting, but if I have some time, I will talk about that. First part is introduction to helical turbulence. And those who are interested in, please look at my very brief review with Anik, published 3 years ago. It's a very, how to say, condensed review, just less than 20 pages, but they include 140 references related to helicity. So at least it should be very useful. And also, especially for transport, I just wrote one chapter in my edited book, helicities in geophysics and astrophysics and beyond. Published from Wiley last year. Okay. Then I think you all know these things, but helicity, very brief things in helicity. Usually, I'm not the fan. I would like to do something like that. And usually people talk about this volume integral of helicity. Then helicity is very often referred to in the context of relaxation problem. But here, I mainly talk about helicity, local density of helicity. Omega is vorticity, U is velocity. Okay. Then first point is that helicity is pseudoscalar. So helicity is not positive definite, and under the inversion or reflection, it's changed its sign. And this is very clear. So if you consider, if you consider the inversion like that, then velocity is polar vector. Of course, velocity changes its component like that. And the helicity also changes because vorticity never changes. Vorticity is the axial vector. So the correlation between velocity and vorticity, helicity also changes. So in this sense, helicity is pseudoscalar. And then, as we can, in mirror symmetric system, all statistical quantity is invariant. But the pseudoscalar should change its sign. That means that pseudoscalar in mirror symmetric systems should vanish. So that means that this very brief argument shows that this pseudoscalar or helicity can be a measure of the breakage of mirror symmetry. Okay, so if you have finite non-zero helicity, you can expect you have some mirror symmetry, breakage of mirror symmetry. Okay, and another point is that this is, of course, well known. I think original argument for kinetic helicity was from Keith Mowat, I think. But then this quantity, volume average, is related to linkage number. Reality is more complicated. Those who are interested in, please look at my previous books. But anyway, so then this quantity can be interpreted equivalent to this type of link. Then the helicity conservation is related to the number of linkage of two vortex tube is conserved, especially implicit limit is conserved. That means that if the vortex tube start to relaxing, then it has some constraint. Then it gives some constraint for the energy dissipation. This is very, very, how to say, simplified argument. But you can easily see, due to the conservation property of kinetic helicity, you have some constraint on the energy dissipation problem. And also, such argument can be also considered if you consider the induction equation for vorticity like this. And this is very similar to the magnetic induction equation. Of course, this is intrinsically nonlinear. This can be sometimes treated as linear. But anyway, very similar. Then if you consider this cosine-sine relationship, then in the presence of kinetic helicity and in the presence of cross helicity in MHD, you can expect some restriction to this non-linear cascading. But this is again very naive argument, but still it gives some suggestions. Okay, so in this sense, kinetic helicity may be related to some suppression of non-linear cascade. And I don't. Please interrupt me anytime you like. I don't mind at all. And this is, again, very old works by mainly fluid physicists. And then people start exploring about high helicity might be related to low dissipation. And this is the original work by Peltz a long time ago, 40 years ago. Then they just consider some places. So dissipation is much, this is the alignment angle between vorticity and velocity. And this is highly aligned case. This is no alignment, and this is anti-alignment. And this is the case of the channel flow. And then if we have a dispersion is greater than 30%, they observe in direct numerics, helicity is much lower. Alignment is lower. And this is the lower dispersion region. Then they found that higher alignment between velocity and vorticity. Then they concluded that high helicity is directly related to low dispersion. But immediately after their work, Rogers and Purvis Moyne made counter validation. Then this is the initial state. Again, this is the alignment. This is again direct numerics. And then developed stage, we have this type of one in total alignment. Then this is a low dispersion cases, and this is the high dispersion case. And you see no essential differences between these two. Then their conclusion is that the relationship between helicity density and dispersion, low dispersion is tenuous. No. Then after immediately 5 years later, some experimentalists, Jim Wallace, did developing a special probe. Then they checked this idea, then confirmed Rogers Moyne's result. Then engineering, if I correctly understood, engineering people stopped considering about helicity because of this one. And they did several situations, not only channel, but also several situations, isotropic, blah, blah. Then their conclusion was no relationship. And the original result is just due to their conclusion, said just due to low resolution, something like that. But anyway, this is one example. And here, I'm interested in large-scale structure in turbulence. Then this is the mean magnetic field equation. And in my talk, capital letter denotes mean field, appropriately defined mean field, and the primed one is fluctuation around it. Okay, then this is mean magnetic induction, and then we have electromotive force, electromotive U prime cross B prime. And the mean vorticity equation in solenoidal case, in complex case, you have this vortex motive force. Again, very similar relationship. And it comes from the velocity equation. And in the velocity equation, it shows up as a Reynolds class. Reynolds is main topics I will talk today. But as you can easily imagine, this vortex motive force, or someone call it ponder motive force, is directly or exactly related to vortex motive force in this form. So if you take one higher derivative of Reynolds stress, you will get vortex motive force. So this is the exact relationship. Okay. Then if you know some information about Reynolds stress, you can say something about vortex motive force, which lead to the large-scale vorticity generation. In the same sense, if you know some information about the electromotive force, then you can say something about large-scale magnetic field generation. And also, another interesting quantity is mean scalar. So then you have turbulent scalar flux. This is the final topics I may be able to talk. Okay, then let me very briefly talk about turbulent transport. And then this is a laminar pipe flow. This is a Poisson profile. It is a parabolic. This is a rare case. We know the analytical solution of Navier-Stokes. Everyone knows that. But in turbulent state, we have this much more complex structure. But this is instantaneous field and this is mean field. Then, as you see, if you compare mean field profile and laminar profile, we have very flat profile. This is just schematically depicted. So then we can easily see, due to the strong turbulent mixing, no inhomogeneous flow is allowed in the main portion of the flow. All inhomogeneity of this axial velocity profile is concentrated in so-called boundary layer. This is a typical one. Then if we consider mean velocity equation, of course, we have a Reynolds stress, and the Reynolds stress was modeled by Lucine almost 150 years ago. So this is so-called eddy viscosity representation. And Bushinet himself didn't give any expression for the eddy viscosity, and we had to wait for Prandtl. So as you know, this year is 100-year anniversary of Prandtl's mission in the same sense as quantum theory. But anyway, so then if you substitute this expression to here, you will have this expression. So molecular viscosity is enhanced by turbulent viscosity coefficient for this mean velocity strain rate. Then first point is that due to this molecular turbulent viscosity, effective viscosity is strongly enhanced. This is a very important point. But another very important point is that unlike nu T is not uniform. Of course, nu itself can be non-uniform, but nu represents molecular viscosity represents property of material. But nu T is represents property of flow. This means that nu T is not at all uniform, not at all in general. That is the reason why we have this type of flat profile. If you just enhance viscosity here 1,000 times, you still have a parabolic profile. Okay, due to the similarity of equation. So this means that turbulent viscosity itself has a strong spatial and sometimes temporal dependence. This is very important. I think, if we consider effective viscosity due to turbulence in realistic turbulence. Okay, sometimes people just increase the effective viscosity by hand, say 1,000 times or something like that. But as long as they use a uniform one, it doesn't, in general, it doesn't represent the property of turbulence. Okay, this is a very important point. Okay, this is a very big thing. And then, but this is already turbulent case, but if we impose rotation, pipe itself is fixed, and the swirling flow is using propeller or vane, we impose the rotation flow in addition to axial flow. Then axial velocity profiles changes, something like that. And also if you just rotate the pipe itself, it is called axially rotating pipe flow. In such a case, this flat profile becomes something like that. So some people consider this is the re-terminalization or something, but fluid state itself is strongly turbulent. So then, if we have a proper model, such model should properly represent this type of. But unfortunately, or fortunately for theoreticians, usual eddy viscosity model never could represent this type of change of behavior because eddy viscosity itself is too strong. Then it immediately, even if we start this type of profile in the inlet region, it immediately relaxes to this type of very flat profile. So in this sense, Reynolds stress represented by eddy viscosity is too strong. Then we need something other which can suppress such effect. Okay? So now I am finishing the introduction. And then I will talk about helicity. So how much helicity affects the turbulent transport. This is one point. And how the helicity effect can be incorporated into the turbulence modeling. And validity of the helicity subgrid scale model. So that work was done with Anik and Pablo Minini and some colleagues. And also such relevant how much it can be related to solar angular momentum transport. Actually, this part was, how to say, inspired by Matthias. I think it is more than 10 years, more than one solar cycle before. Anyway, okay. Then kinetic helicity effect. I will not talk about the detail of theoretical formulation at all. So, but again, long time ago, actually, this is almost my first paper when I was a master course student. But inhomogeneity, anisotropy, and non-equilibrium property of turbulence is somehow implemented in the theoretical form. Mirror symmetric case was done first, originated by Yoshida, my mentor. And the non-mirror symmetric case I did for the first time. And this is a combination of, as Mosumi mentioned, so direct interaction approximation, so elaborated classical theory of closure of homogeneous turbulence in the combination with multiple scale analysis, I think originated by Poincaré, I think, basically. Then we introduced here two scales. So with scale parameter delta, this is delta x and delta t is not necessarily same, but later analysis we just use the same delta. But anyway, if delta is very small, this x and t is original variable. But if delta is very small, capital X and capital T is good variables, which represent slow and large scale motion. Because only when original X changes considerably, capital X and capital T starts changing. So in this sense, capital X and T is called slow variable, and Guzai and tau is called fast variable. Then field quantity is divided into the mean part, which depend on slow variables, and also fluctuating part, which depend both on fast and slow variable. Then, due to this dependence of capital X and capital T of fluctuating field, we can treat inhomogeneity of turbulence. This is a very good point. This is a typical analysis of two-scale analysis. Then all derivative, spatial and temporal, can be just due to this introduction of two-scale is written like that. The point is that if you have large-scale inhomogeneity in space and time, it shows up with delta. Then original equation is written. This is, again, simplest solenoidal case, but show up like that. And all large-scale inhomogeneity show up with delta. And even solenoidal condition, divergence U should be written in this form. But again, point is that all inhomogeneity and anisotropy and also some non-equilibrium have to show up with some scale parameter delta. Okay, and the left-hand side, without delta is basically exactly the same equation as homogeneous turbulence. Then we can use such legacy of homogeneous turbulence theory. Okay. Then lowest order fields. Then we expand. This is a typical way of theoretician do. So we expand the field quantity with scale parameter delta. Okay, and the lowest order field, again, homogeneous isotropic. But isotropy is not necessary. So we need homogeneous one. Okay, but if we also assume isotropy, the mathematical treatment becomes much, much simpler. But anyway, then lowest order field is again homogeneous isotropic. Then if we consider the velocity correlation, U prime, you get 2.2 times correlation of fluctuating field. Then in homogeneous case, it just depends on the displacement. Okay? Like this. Then this is a physical picture. This is the longitudinal correlation. R is displacement. And this is transverse, and this is cross correlation. Okay? Then, as you see, in non-mirror symmetric system, this plays very important. In mirror symmetric system, this correlation and this correlation just cancel each other. So then we have no contribution here. But in non-mirror symmetric system, this should be considered. This is my message. Okay. Then if we construct utilizing some arbitrary vectors A and B, if we construct a scalar which is isotropic, I mean the invariant under the rotation, then this is the generic expression because it should depend on vector A and vector B and vector R and it's their angles. So this is a very generic expression. If you are interested in, for example, many classical textbook shows this. For example, Marshall Schultz textbook also explains this type of thing. Then, if we take A and B is how to say unit basis vector, then you will get this type of one. So this can be expressed like that. So this is a very generic expression for the homogeneous isotropic velocity correlation. And these two parts is actually related to Kalman-Haworth equation, directly related, if you know Kalman-Haworth theory. So this is a configuration space, as I already mentioned. And in wave number space, it can be written in this form. Then this is compressible energy related part, compressible energy spectra. This is solenoidal energy spectra, and this is related to helicity. Again, this cross flow interaction, which is directly related to helicity. And if you neglect that part, you will kill the possibility of helicity. Mirror symmetric system, it's okay. But non-mirror symmetric system, at least we should retain this part. Okay. But this is just for lowest order field. So we assume that this very generic form for the lowest order homogeneous isotropic turbulence field. Then all other inhomogeneity, anisotropy, and non-equilibrium property terms enter with higher order. Okay, then just labor stress analysis that I did. So then, long time ago, again, more than 40 years ago, and this is lowest order field, and all inhomogeneity show up with these higher order term. Then random stress can be expressed in this form. Again, without that part, this part is just Bushinet did 150 years ago, just by intuition, I mean, empirical thought. But from fundamental equation, we can obtain this type of one. And this part is symmetric part of velocity shear. S is mean velocity strain, and omega is mean vorticity, which is an anti-symmetric part of velocity shear. And also system rotation also enter in this form. So relative vorticity and system rotation, this is so-called absolute vorticity. Absolute vorticity. Then transport coefficient nu t is in this formulation, is written in this form. Sorry, I did not tell anything about response function formulation and also spectral formulation, but this is energy spectrum, solenoidal energy spectrum. This is green function. So green function gives how much past influence the present state from minus infinity to the present time. And if you can evaluate this part independently, in the simplest case, this part, that means that energy spectrum doesn't depend on the temporal evolution. But anyway, this just gives the time scale of turbulence. This is time scale, and the other part gives energy. So in the simplest possible case, this gives time scale multiplied by energy. And this is actually the mixing length expression, Planck gave. But this is, you see, this is a very generic expression for the eddy viscosity from the fundamental equation. And this is already okay, but here we also consider that this cross flow correlations. Then not only symmetric part of velocity share, but also anti-symmetric part of velocity share should enter the expression. Then transport coefficient gamma is a vector, is related to gradient of Helicity, but this gradient is not a small scale gradient. This is a large scale gradient. I skipped that detail. Then Helicity homogeneity is essential. Helicity homogeneity. These theoretical results already suggest, in addition to the eddy viscosity type expression, we also should consider the helical property of turbulence if we start consider the non-mirror symmetric system. Okay. Probably I should skip the detail, but in our formulation, it shows up something like that. This is complicated, but this is velocity share, mean velocity share. This is system rotation related. And this has a symmetric part and anti-symmetric part. And the symmetric part coupled with, this is a first order field. With green function, we can formally solve first order field sorry, because I skipped. Green function is originally for this one. And this right-hand side can be treated as a four-star. And if you know some information about green function, you can formally solve higher order field. Okay. So, but anyway, then first order field can be solved in this form with green function and the spectral. Then if you multiply U0 here, then U0 is multiplied here. So U0, du dx show up. Something like that. If you have a lowest order field that has an energy related part, as I already mentioned, then you will have this expression with, and this part, and also anti-symmetric part of mean velocity share, then multiplied by U0, and then this part, non-symmetric contribution for the velocity correlation show up for the U0, U1 field. So this is very, very complicated, but very straightforward. So this suggests that eddy viscosity is coming from the combination of symmetric part of velocity share, mean velocity share, and how to say, energy-related correlation part. This is how to say, source or origin of eddy viscosity. And Helicity effect is related to anti-symmetric plus rotation. of the system coupled with uh, cross correlation. Then we have this expression. This is a bit detailed, but okay, then I did already became tired, but okay. So then, but the original equation is too heavy for practical use because it uses green function and spectral, so too heavy for practical use. Then we consider just utilizing that expression, consider nu-t should be related to time scale multiplied by energy. And the Helicity gradient coupled with vorticity and eta is also something like that. Then we can construct this type of one point statistical quantity. That's current energy, dissipation rate, current helicity, and depending on station, we can also consider Helicity dissipation rate. Then we apply this simplified turbulence model for swirling flow situation. And this is a result long time ago. Then this solid line is in inlet region. Inlet region, we have dent profile. Dent profile itself can be interpreted because of centripetal force. So flow is pushed to outward direction. And in order to locally conserve the angular momentum, somewhere we need some angular momentum flux. Somewhere we have some deceleration. It occurs in the central part. This is a very laminar picture. But anyway, this type of dent profile cannot be, as I mentioned, could not be reproduced in usual K-Uction model without this blue part at all, as I mentioned. It immediately relaxes to the usual type of profile. But with this Helicity effect, we could reproduce this type of dent. This is, of course, matter of course, because we add additional term with one model constant. That's better than disagreement. Okay. So, but usually engineering people just without knowing this stuff, people just reduce the model constant just a few percent of original one. Then they could reduce the very strong eddy viscosity effect. That was the reality of engineering field. But this is more physical because we have swirling flow with Helicity. Okay. And this is one example. And very recently, not recently, almost 10 years ago, I asked Axel Brandenburg to check this idea with very simplified box simulation. Then as you remember, ingredient is some rotation or like vorticity and inhomogeneous Helicity. The inhomogeneous Helicity is externally imposed in this simulation. Two direction X and Y is statistically homogeneous and Z is inhomogeneous. Okay. Then we did direct numerics, and this is the Helicity profile in Z direction, and this is the gradient for Helicity. Then in addition to that, we impose rotation in Y direction. Okay. Then all sets. We have rotation, antisymmetric part of velocity shear, and Helicity inhomogeneity. Then we see several situations we checked. And then this is a temporal evolution of current Helicity. As I mentioned, during the whole process of simulation, we have sinusoidal profile of Helicity, positive and negative. This is just given by forcing. Then at the initial stage, we have no large-scale flow by setup. But as time goes by, this direction is inhomogeneous direction, D direction. As time goes by, large-scale flow is generated like this. So without any, how to say, additional forcing for flow. So this inhomogeneous Helicity coupled with vorticity gives this type of large-scale flow generation. And this is early stage of development, and this is steady state of development. Then we check balance. early stage, we have no large scale flow, no velocity here, no vorticity. Then Reynolds stress should be represented by a rotation coupled with Helicity gradient. This is the direct numerics of Reynolds stress, and this is the Helicity gradient. That's a good correlation in early stage of development. And the developed stage, we should have a balancing between this term and this term. Then we will get steady state. Then this one should be balanced, this one. In this particular case, omega is much bigger than omega. Relative vorticity. Then Ui, if we integrate it once with respect to G, generated velocity in the direction of rotation should be proportional to Helicity. And this is generated velocity, and this is imposed Helicity. Again, very nice. So in this sense, at the developed stage, we have very good balancing between eddy viscosity and inhomogeneous Helicity. This is just how to say, simplified numerical test of this effect. But at least in this particular setup, eddy viscosity is not at all good. Alone is not at all good. We have to consider this additional term, which is related to rotation or vorticity coupled with inhomogeneous Helicity. How much Helicity we have is another problem in the realistic situation, but at least. And this is some kind of physical interpretation which is related to Reynolds stress is very important, but this is tensor. So then we have to also consider the divergence of Reynolds stress to consider momentum balance. So it's a bit complicated. In this particular case, we just prefer vortex motive force, which is vector. And again, Reynolds stress and vortex motive force is one-to-one relation we have. Then this is mean vorticity equation, so vortex motive force show up here. Then if we, vortex motive force, if we substitute the Reynolds stress expression here, we have this expression here. So this nu T, eddy viscosity term, if you substitute this here to here, it just enhances molecular nu. This is quite natural. Eddy viscosity just enhance destroying process of large scale vorticity. But we have this term. This term is related to one higher derivative of Helicity. That means that Laplacian of Helicity. So then if we anchor, this argument is very naive, but anchor this equation, then delta U should be proportional to vortex motive force. You think this is very dubious. Actually, I myself consider dubious, but this is one possibility. Then, if we approximate Laplacian in this form, then it gives this type of picture. If you have some non-trivial spatial distribution of turbulent Helicity, some localization of turbulent Helicity, then with rotation or large-scale vertical motion, then it gives large-scale flow, possibility of large-scale flow in the direction of large-scale vorticity or rotation, depending on the sign of Laplacian Helicity. Then, with minus sign, if you have vorticity in this direction and this type of convex distribution of turbulent Helicity, it should induce large-scale flow in the direction of rotation. Actually, it occurred in numerics, direct numerics. So this is rotation is in this direction. So we observed large-scale flow generation, spontaneous large-scale flow generation. But okay. So please stay with me. Okay. So the vortex motive force. Then what we should do is that velocity fluctuation equation and multiply omega prime in outer product force. Then we can consider this type of thing. Then if we assume this type of positive helicity, kinetic helicity, then we have statistical alignment of U prime and omega prime. And due to this term, I mean, this is due to the local angular momentum conservation associated with this type of rotation of vorticity. Then flow is induced in this direction. Then we can construct vortex motive force in this form. This gives a parallel contribution if helicity is positive. But this is not true. If you consider the other part, vorticity equation, this is again exact formulation. Then again, we just assume positive kinetic helicity. And this means that along the direction of large-scale rotation of vorticity, if you have a velocity variation, you have flow induction in this direction, vorticity induction in this direction. Then it gives the anti-parallel contribution. So both for the positive kinetic helicity, these two terms cancel each other, at least qualitatively. That is the reason why presence of helicity, kinetic helicity itself is enough. We need some special distribution of helicity. That point I will skip, but this is another point is that because Reynolds stress is U has minus parity. U is actual polar vector. U is polar vector. So Reynolds stress is pure scalar, as pure tensor, usual tensor. Then this is minus, and energy is plus. So in this sense, this part is okay. But without gradient, this is actual vector. Helicity is pseudo-scalar. So this is plus and minus. Then it doesn't match the parity of Reynolds stress. So in this sense, we need gradient of helicity or integral of helicity or square of helicity or blah, blah, blah. If we just naively consider such parity argument, helicity itself cannot enter the Reynolds stress expression as a coupling coefficient for the vorticity. Okay, so then finally, stability scale model. Probably now with Anik and Pablo and Yuan Rosenberg and Rafael Manini, we are doing this. And one of the purpose of my visit here is just keep working on this one. But not necessarily physics of fluid. I don't know which journal I should, but we already finished the first manuscript draft. Anyway, I think I don't need to explain the subgrid scale modeling, and this is, okay, I will finish very soon. So then this is a so-called subgrid scale modeling with some filtering. So this part is unresolved, and we need modeling of this small scale eddy with large eddy simulation. Then Smogensky considered this statistical property of this part can be expressed in terms of filter. Filter is the largest scale of unresolved scale, and the strain rate of grid scale. Okay, this is the basic idea of Smogensky. I will skip dynamic procedure. Then, but Smogensky model, and even with dynamic procedure, we still have such problem. So for isotopic flow, mixing layer flow, channel flow, Smogensky model CS model constants should be changed. This is not at all good. And As you see, isotropic case is about 0.2. This case is 0.1 with square dependence. This means that if you adopt 0.2 for here, it's too much dissipated for channel flow. Okay, this is the reality of Smagorinsky model. So I really respect Smagorinsky, but at least application of Smagorinsky model for this type of very simple flow is not at all good. Then Germano consider dynamic procedure, but still, if we have streamwise vorticity, dynamic Smagorinsky doesn't work. Then, if we consider the vertical structure, so isotropic case is not strong compared to the wall turbulence case. Wall turbulence case, you will have this type of streamwise vorticity, strong streamwise vorticity. Then my guess, long time ago, is that need for the drawback of Smagorinsky model should be related to this type of vertical structure. Then, in addition to the usual Smagorinsky model, we also should consider the Helicity effect. That's a basic idea. And but in addition to the original one, we need to solve subgrid scale energy equation and subgrid scale Helicity equation. Blah blah blah. This is one possibility, and also another possibility that if we assume local equilibrium of energy production should balance energy dissipation. In such a case, we can eliminate one equation. Then all quantity is expressed in delta and S. S is grid scale strain rate and subgrid scale Helicity equation. Subgrid scale Helicity equation we still have to solve. This is one equation Helicity model. But the Smagorinsky model has zero equation model. Then in order to do that, we also have to consider the local equilibrium of Helicity production should be balanced with Helicity dissipation. If we assume all these things, then we can construct zero equation model. All quantity is expressed in terms of grid scale quantity and delta. So this is the same level as Smagorinsky. Okay. Then our intention in direct numerics with ghost. So sorry, Nick, I have not enough time to explain. But then we did some direct numerics to validate this idea. So this is Helicity is imposed by forcing, helical forcing with Pouquet-Patterson formulation. Without changing energy, we impose some inhomogeneous Helicity. And this is temporary evolution of energy and entropy. And this is the energy spectrum, Helicity spectrum. Then we use this steady state, precise steady state for statistical analysis. Okay. Okay, I will skip that, but we have some balancing between production mechanism of Helicity and dissipation mechanism of Helicity in this sense. And those who are interested in, please look at our forthcoming paper. And anyway, then we did this type of scattering plot. So temporary evolution, but we just took the data from the steady state. Then we plot some average quantity, and this is, for example, model expression and direct numerics. And this is, for example, this is energy dissipation rate in case, and this is model expression. This is velocity cubic divided by filters. This is a very famous Kolmogorov expression. Then this is a model, this is a direct numeric. So we have a rather good correlation. This shows that energy dissipation can be expressed in this simplified model expression. And also Helicity dissipation rate again, very good correlation. So in this sense, this suggests in this particular setup, we can use simplify the algebraic form of dissipation rate. And the color means how much helicity gradient we have. So for we have helicity gradient here. So this part is represented by yellow. That part is represented by blue. Anyway, then as you can easily imagine, this part very strong gradient of helicity. Value of helicity itself is very small. So then this is concentrated here. So then our major result is this one. This is Smagnitsky model. And this is off-diagonal component, which is very important for constant. And this is direct numerics, and this is Smagnitsky. And not at all good correlation. But with the helicity term, much improved. So in this sense, in this particular case, helicity term plays very important role for reproducing the direct numeric. This is a summary of this part, but the main point is that helicity term contribute improvement of the correlation between DNS and the modeling term. And also algebraic model can be used. Finally, this is with MacMish. So you know all these things. So this is a helioseismology results. Then I will skip this part. And there are some conundrum, convection conundrum. Some turbulence people, York, Schumacher, and Srini did this type of review paper. And the main point is that this is large scale, this is small scale. And the large scale fluctuating motion is much smaller in observation compared to numerics, mainly ash code, blah, blah. So this is one point. Another point is that the differential rotation profile, usually we need prograde profile for solar rotation. But if we adopt solar parameters, we will have anti-prograde, not anti-prograde, but not prograde profile. This is another problem. And also another fundamental one is that if we have not strong enough fluctuation in large scale, how much we can reproduce strong heat transport. This is another problem. Then there's, I think, in my opinion, there are three approaches, roughly speaking. One is rotation effect. This is a bit related to helicity. And another one is magnetic field effect. For example, Hideki Hotta, I think, stresses this part. And I myself consider cross helicity plays very important, but that's we will not talk here. And another effect is coherent motion effect. If you have a volume motion, tomorrow at CU, I will talk that part. But anyway, then my point is that, as I already mentioned, I will finish in four pages. Is okay? So then we have a meridional circulation. It is, how to say, persistent rotational motion. In addition to that, we have this type of helicity spatial distribution, typical in several numerics. And we can guess this type of profile. This is very typical profile. The combination of inhomogeneous turbulent helicity with large-scale meridional circulation, we can expect some deceleration or acceleration due to this inhomogeneous helicity. And as I mentioned, if we have a Laplacian helicity with meridional vorticity, then we can expect this type of flow generation, as I already mentioned. And this is a mean vorticity due to meridional circulation. This is from screen to you. And with this profile, this gives, how to say, a positive contribution due to this one. Then it gives this contribution, acceleration here. So qualitatively, it is good. It is good. So in addition to the eddy viscosity type term, which destroys such spectroscopy, if we have helicity homogeneity, which couples with meridional circulation, it may contribute to the angular momentum transport, which is preferable for progress. This idea was inspired by Matthias long time ago. But anyway, then I asked Mark to check. And in the paper, I already published with Mark in geophysical astrophysical fluid dynamics this year. Then this is helicity, and this is turbulent helicity and helicity gradient and meridional vorticity, azimuthal vorticity due to meridional circulation. This is helicity, inhomogeneous helicity. This is the Reynolds stress. And then alpha component, which contribute to the phi angular momentum transport. And the basic pattern is the same, apart from this complicated vertical structure. This part is red, except for this one. This is red, and this part is red and blue. So in this sense, good, if you accept. And then I also asked Mark to check the magnitude in his calculation. And the Reynolds stress is 10 to the 9, and this part, and so with solar parameter we adopted, it's 10 to the 12, but actually the simulation suggests the C eta should be 10 to the minus 3 or something. So this gives a comparable contribution. And also for theta phi component, again, comparable. This is good. If this is just 10 to the 5, no chance. But this is comparable. So in this sense, we are happy. Then, okay, I will skip that part. This is very interesting, but later I can discuss with this. But this gives some possibility of energy transport, not parallel to gradient of temperature, but perpendicular to the but anyway, okay. Thank you for your patience. This is some role of helicity stochastic and cross-related not. Oh, sorry, this is not good or good. And finally, it's advertisement. So this is a book. So many magnetic helicity arguments is here. And small kinetic helicity and current helicity effects here. Kirill Kuzania and Manolis Gregorius and Rodion Stepanev edited. And also MHD, please look at my review paper, and also important paper with Amin. Thank you very much for your patience and data. Thank you.
Select talk. So questions now? Yes. Yeah.
Regarding the last part, you talked about the angular momentum transport. How do these helicity effects you have here relate to the lambda effect, which is what Schwitter, Rüdiger, Leonid, Pichatinov have been discussing for a long time for the angular momentum?
Yeah.
Are they more or less the same, or are they fundamentally different?
Oh, it's a bit difficult. Actually, in the paper with Axel, I argued about the difference between this effect with lambda effect and difference between this effect with Uriel-Frisch Aka effect. And for the usual lambda effect, theoretically, it is just a kind of ansatz. So Reynolds stress should be in terms of rotation. and the transport coefficients should be written lambda 1, lambda 2, blah, 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 blah. So this is a big difference. We can derive it from the fundamental equation. And when I talked with Leonid Kichachinov about this effect, he said their lambda should be related to helicity. In this sense, I agree with him, because if you have a Reynolds stress expression which is proportional to vorticity or rotation, the transport coefficient should be related to helicity, close correlation at least. But as I hope I clearly show it, helicity itself is not enough. We need a helicity gradient. So in this sense, relationship between famous lambda effect and this effect is a bit.
Oh yeah, these GSI, they use it differently.
Okay. Is a bit difficult, but their work was, I think, 80s and 90s, and also some very early work was even 70s, I think. And our work was 90s, early 90s. So, but that's all I can say.
Yeah.
But theoretically, this is not at all answers. This is just coming from, we know the analytical expression for the lambda, our gamma. I don't remember the, yeah. So that's the point. Then my suggestion for solar people is just how about calculating helicities, spatial distribution, and also explore the generation mechanism of helicities. We know the transport equation for helicity, and we can compare it with. Actually, one of the purpose of with Pablo's work, I skipped that part, but for example, we know transport equation for helicity. And in fact, situation, we have helicity production, helicity dissipation, and helicity transport, we know. Then if we compare helicity, spatial distribution of helicity itself with each term, each contribution, it already gives very informative result, I think. Yeah.
Yeah, please, Sandra.
I have a theoretical question and a practical question. So
Yes, thank you.
my theoretical question is kind of general, just to get a handle on what you're doing, because you're doing separation of timescales. So does this obey a fluctuation dissipation theorem, or if not, could you construct it to do that when you do this separation of timescales?
Theoretically.
Yeah, all the stuff you do, all this lovely development. Yeah.
This delta is, if delta is very small,
Yeah.
we have well scale separation.
Yeah.
But this delta is not necessarily small.
But you can always do, fluctuation dissipation theorem, you can always do the decomposition,
Yeah.
even if they're not well separated, and you will get a fluctuation dissipation relationship out.
That's true. But another point, or maybe difficulty of fluctuation is that turbulence itself has no such distinct scale separation.
Exactly. Yeah, I get that. That's what I'm asking. Yeah.
Then I think it's a rather difficult, but I prefer Poincaré method because this delta is not necessarily small.
No.
And finally, it's just eliminated in the final expression. I did not explain that.
No.
So in this sense, it's a bit tough, but still, DIA, direct interaction approximation for homogeneous turbulence, homogeneous isotropic mean. They both Krajina considers how to say renormalization.
Yeah.
Then all the terms of
Yeah.
deviation from the Gaussian and infinite path
Yeah.
implemented.
Yeah.
But this theory contains, as you noticed,
Mm.
two types of expansion.
Yeah.
One in the same sense as Bob did,
Yeah.
renormalization.
Yep.
And the second one with scale parameter
Yeah.
delta is not renormalized.
Exactly.
Yeah.
Yeah.
So in the sense, validity of that one is only tested by,
Yeah, just looking at the simulation and what have you. Yeah. Okay.
but at least if you accept or adopt eddy viscosity type of expression for labels,
Yeah.
yes, or some gradient diffusion or something, then this type of some correction change should be considered
Okay.
in non-mirror symmetric case. That's my message.
Okay.
And also, fluctuating dissipation, a long time ago, I considered for formulating that, but again, the problem is how to treat all the scales
Mm.
in between.
Mm.
That's always a problem, even homogeneous tablets.
Yeah.
Thank you. And practical.
No, it's interesting. Practical question. Well, just thinking about the sun. So,
Yes.
and helicity. So, you've got these bands of sunspots which are kind of doing their solar cycle thing, and it's usually people take measurements around. That's where there is more shear. So I was wondering about this picture. It's not in that picture, but if you look at, is it possible to look in data to try and understand how the dynamo?
Mhm.
I'm trying to think, can this tell us something about how the dynamo works? That most of the shear, probably the helicity is carried in the sunspot bands. It's not uniform. It's not nice and smooth. I'm just wondering if there's something in that, to relate all this stuff to dynamos working, because that's a thing, right? And you've got this. That's where the shear is happening.
Yeah.
It's in the sunspot, bands, and they're kind of doing their thing and then annihilating, So I'm trying to relate this to understand how the dynamo and the sort of overall sunspot, the solar cycle is kind of going into this
I think
picture.
there are some finite helicity.
Yeah.
That point I'm quite sure.
Yeah.
In the same sense, some helicity is present in the cyclone and tornado. Also, some solar tornado structure of course we have. And long time ago, I discussed with, for example, Sasha Kosovichev, but I'm afraid it's not in the context of kinetic helicity, but cross helicity.
Sure.
Cross helicity, so then we have sunspot and this type of motion.
Yeah.
Umbrella, something like that, motion. And also, they observe some. Oh, sorry, I don't remember. I have.
Sure, yeah, but there's.
So I think it's a very interesting
There's something.
topic.
Yeah.
But another difficulty at the time is that just a real measurement.
But now they've got really nice measurements.
Things. So
There's some really nice observations.
10 years or 20 years. Yeah, I think so.
Yeah.
Yeah. So then, of course, unlike energy is positive definite.
Yeah.
But the helicity is non-positive definite. So sometimes strong positive.
But this is
sometimes
the story.
depending on resolution.
Yeah, but that's
It's just
Oh,
so that was the difficulty.
yeah, but I think.
But if we have some non-mirror symmetry,
Yeah.
breakage mirror symmetry, as I mentioned,
Yeah.
helicity is actually a measure of such quantity.
Sure.
Then, if we take appropriate averaging or appropriate statistics, we should have that one.
Yeah.
Then actually in this particular case with Mark Mesh result.
Well, he will get. That's what I'm thinking. He's got his hands on this stuff.
Yeah.
Probably give you something.
Yeah.
That's a bit more. There's quite detailed observations now of this stuff. So
But I think
Both the
in
kinetic helicity.
the presence of such rotation motion.
Yeah.
So then usually people just argue about the velocity shear.
Yeah.
Velocity shear.
Yeah.
But for me, symmetric part and division of symmetric part and anti-symmetric part
Yeah.
is crucial.
I get that.
Crucial.
Yeah.
And the symmetric part coupled with energy.
Yeah.
Anti-symmetric part coupled with this type of
Yeah.
pseudoscalar. This is obvious, theoretically obvious. Then if some measure in person or numeric.
Well, I mean, I think, you know, this is not my data, but I think there's some really nice data out there. You could,
Yeah.
you know, to do some things on this. That'd be really, I'm not going to do it. I'm just, you know, encouraging you to do it. I think it'd be interesting to try and understand all this, you know, how it relates to the overall, you know, solar cycle dynamo stories. It'll be really interesting. Yeah.
Yeah. Thank you. Thank you for your comments.
No, it's interesting stuff.
Appreciate it. Yeah.
Other questions?
I will be here until Friday, 3104. So you are most welcome.
Yeah, we're here for a few weeks, so yeah, we as well. So yeah.
Tomorrow I have a talk at
Southwest.
Southwest